So, gonorrhea is a disease that no one wants to get. It's very unpleasant, but for most of our lifetimes, it hasn't actually been dangerous. 15 years ago, there were 5 different antibiotics that could be used to treat gonorrhea, and any one of them was highly effective. Today, there's only one. The evolutionary pressure of antibiotics has caused gonorrhea to become resistant to the other 4. And recently, we've started seeing cases of supergonorrhea, which is resistant to all 5. This is a problem. And it's not a problem unique to gonorrhea. Pretty much every infection that's historically been treated with antibiotics now has antibiotic-resistant strains. And antibiotic resistance tends to emerge fairly quickly. If you look at this timeline, the top shows when all the important antibiotics were discovered. The bottom shows when the first bacteria became resistant to those antibiotics. And you can see that's typically a matter of less than 5 years before an antibiotic starts to face resistance. And the rate at which bacteria are becoming antibiotic resistant is only increasing. So in the next decade or 2, we may see antibiotics become completely obsolete against most common diseases. This is a huge threat to public health and national security. So this would be greatly mitigated if we could just keep discovering new antibiotics, discover enough in the near future to replace the 100 or so that are becoming obsolete. But we're not on track to do this. We're discovering 1 or 2 new antibiotics in a good year. And that's because the antibiotic discovery process is incredibly slow. Right now, we'll take large sets of molecules and just test each molecule against bacteria, hoping that something works. And usually nothing works. It's like looking for a needle in a haystack. So what would be great would be if we could identify the most promising candidates and only test those. That way, we'd be looking for a needle in a smaller haystack. But that's way easier said than done. You see, we're actually really bad at predicting whether or not a molecule is going to be a good antibiotic. And that's because an antibiotic needs to accomplish a lot of tasks. First of all, its target is inside the cell, but the antibiotic starts off outside the cell. And the bacterial membrane is specifically designed to keep strange molecules out. And even a molecule can get through the membrane. Gram-negative bacteria have something called the efflux pump, which binds to toxins and removes them from the cell. So a successful antibiotic needs to somehow permeate the membrane, then avoid the efflux pump. These are very complicated processes, and we actually don't have a very strong understanding of the chemistry behind them. So it's incredibly difficult for us to predict whether a molecule will be a good membrane permeator and whether it will be a good efflux avoider. I hope to use computers to make these predictions for us. This summer, I have been designing a machine learning algorithm that can take several inputs that describe a molecule and use them to predict where that molecule will permeate the membrane and whether it will avoid the efflux pumps. The main challenge of this has been figuring out what inputs to use. Right now, we have about 150 different quantities for each of our molecules, describing everything from size to shape to charge to the interactions it has with other molecules. But the vast majority of these probably have nothing to do with permeation or efflux avoidance. And to get a successful machine learning algorithm, I need to identify the handful of inputs that are correlated and use those. So this has proven more difficult than expected for efflux avoidance. I actually haven't found a good set of inputs for that yet, although I'm still working on it. But for permeation, I have found a set of inputs that gets me up to about 80% accuracy, which is better than what we have before. And the cool thing about these inputs is that almost all of them are related to the interactions that the molecule has with the molecules that make up the cell membrane, which makes sense. Those are the interactions that are going to be happening in the permeation process. So this is great for 2 reasons. First of all, now that we see which specific interactions are correlated with permeation, that gives us a much stronger idea of what interactions are happening during the permeation process and could inform future models. But I've also demonstrated that it's possible to use machine learning to predict permeation. Now, 80% is not as high as we would like it to be. We wouldn't be able to use the algorithm we have right now. But I'm also using logistic regression, which is not a very good machine learning technique. But now that we know what inputs to use, it wouldn't be that hard to use those same inputs to train a much more complex machine learning algorithm, maybe a neural net, that'll be able to make this prediction to a much higher degree of accuracy. And the great thing about the inputs I found is that all of them can be calculated using computational models. So with this software, no wet lab work will be required to identify the most promising antibiotics from a large set of molecules and only test those. That would cut a huge amount of time out of the antibiotic discovery process and potentially allow us to find the cures to supergonorrhea and other multi-drug resistant infections before it's too late. Thank you.